Hello and welcome. Our subject for this video is going to be Norton and Thevenin Equivalents. So sometimes when we're analyzing a circuit, we're only interested in what happens at a specific pair of terminals. In this case, we can use Norton and Thevenin Equivalents as a circuit simplification technique to aid us in analysis. A Thevenin equivalent circuit is an independent voltage source, which we will call VTH, or Thevenin, in series with a resistor that we will call RTH, or Thevenin, which replaces an interconnection of sources and resistors. This series combination of Thevenin and Thevenin is equivalent to the original circuit in the sense that if we connect the same load across the terminals A and B here, we will get the same voltage and current at the terminals of the load. To represent a circuit by its Thevenin equivalent, we must first determine the Thevenin voltage, Thevenin, and the Thevenin resistance, Thevenin. To accomplish this, we simply calculate the open circuit voltage, or when the load resistance is infinitely large. On the other hand, if the load resistance is 0, this gives us a short circuit condition. So if we place a short circuit across the terminals A and B of the Thevenin equivalent circuit, then the short circuit directed from A to B is going to be I of the short circuit equals Thevenin over Thevenin. In rearranging this formula, you'll find that Thevenin equals Thevenin over the current of the short circuit. Thus, the Thevenin resistance is the ratio of the open circuit voltage to the short circuit current. So looking at the circuit below, to find the Thevenin equivalent of this circuit, we first calculate the open circuit voltage, which we'll denote as VAB. Notice if you look near the terminal A, because the terminals are in an open circuit configuration, there's actually no current flowing through the 4 ohm resistor. Therefore, our open circuit voltage, VAB, is going to be identical to the voltage across the 3 amp current source. So we can label that right here as plus or minus in V1. So using nodal analysis, we can solve for this V1. So you're going to take V1 minus 25 over the 5 ohm resistor plus V1 over the 20 ohm resistor, and then minus 3 amps because of the direction, and this is all going to be equal to 0. Solving for V1, you're going to have V1 equal to 32 volts. So now that we know that, our Thevenin voltage for the circuit is going to be 32 volts. So the next step is you're going to place a short circuit across the terminals A and B and calculate the resulting short circuit current. So we're going to solve for a new voltage, and we're going to call this V2. I'm just going to put a plus and minus right here. We'll call this V2, okay? And we'll have ISC, which is our current of our short circuit right here. So solving for V2, we're going to have V2 minus 25 volts divided by the 5 ohm resistor plus V2 over 20 minus 3. And now because of the short circuit condition, we're actually going to have another circuit component. So we're going to have plus V2 over the 4 ohm resistor is all equal to 0. Solving for V2, we're going to get V2 is equal to 16 volts. Now using our equation from earlier, we can calculate Thevenin, which is Thevenin is equal to Thevenin over the current of our short circuit, and the current of our short circuit is going to be equal to Thevenin over Thevenin. Therefore, our ISC is going to equal 16 volts over our 4 ohm resistor, which is going to equal 4 amps. And plugging into the other formula, we're going to have V Thevenin, which we calculated to be 32 volts. And we're going to have 32 volts divided by the 4 ohm resistor. It's going to be equal to 8 ohms. So now if we want to redraw our circuit in the Thevenin equivalent, we would have our 32 volt source with our 8 ohm Thevenin resistance, the terminals A and B. So to check our answer, we can do some source transformations instead of doing the Thevenin equivalent to see if we can get the same answer. So looking at the top left figure, this is our original. So if we look at the circuit in the top left and we take the 25 volts and we divide it by the 5 ohms, because we know that the current is equal to the voltage divided by the resistance, you're going to get an equivalent source transformation of 5 amps. So if you look at the bottom left figure, the source transformation is a current source of 5 amps that we just calculated in parallel with a resistance. And this is how we do source transformations. Next, we can combine some parallel resistors. So if you take the formula for resistors in parallel, our equivalent resistance is going to be 1 over the 5 ohms plus 1 over 20 ohms, and your final answer is going to be 1 divided by all of this, which is going to equal to 4 ohms. Next, because we have 2 current sources in the same direction, parallel, we can combine these 2 sources, which is going to be our total current. It's going to equal first current plus the second current, which is equal to 5 amps plus 3 amps, which is equal to 8 amps. So if you look at the top right corner, we have the equivalent circuit of our 8 amp source with our 4 ohm equivalent resistor. So now that we see we have a current source parallel with a resistor, we can do another source transformation. So we know that V equals IR, so 8 amps times 4 ohms is going to be 32 volts. So the figure in the bottom right hand corner, you're going to have 32 volts, and then you'll have 2 4 ohm resistors in series, which we just know we can add together, and that's where you get the 8 ohms. And as you can see, this answer is the exact same Thevenin equivalent that we reached before. So before we move on to the next section, we can do one last source transformation on this Thevenin equivalent circuit. So if you take 32 volts divided by 8 ohms, you're going to get 4 amps. Therefore, this final source transformation is going to be a 4 amp current source in parallel with an 8 ohm resistor. This is actually known as a Norton equivalent circuit. It consists of an independent current source in parallel with the Norton equivalent resistance. And just like we did here, we can derive a Norton equivalent circuit from a Thevenin equivalent circuit simply by taking a source transformation. Thus, the Norton current equals the short circuit current at the terminals of interest, A and B, and the Norton resistance is identical to the Thevenin resistance. Take note, while using source transformations, it might have made our life easier in this situation, it's usually most useful when the network contains only independent sources. The presence of dependent sources requires on retaining the identity of the controlling voltages or currents, and this constraint usually prohibits continued reduction of the circuit by source transformations. So let's take a look at an example with dependent sources. Here we have a circuit with a dependent voltage source as 3V and a dependent current source as 20I. So the first step in analyzing this circuit, you need to recognize that the current labeled IX must be 0. This is because there's an absence of a return path for IX to enter the left-hand portion of the circuit. So the open circuit, or Thevenin voltage, will be the voltage across the 20 ohm resistor. So with IX equal to 0, V Thevenin is going to equal the voltage across the terminals, which is going to just be equal to negative 20I, our dependent source, times 25, which is going to equal negative 500I. To solve for I, we can see that it's denoted in the top left-hand corner. You're going to take I is equal to 5 minus our dependent source, which is going to be 3V, divided by 2K. Upon writing this equation, we realize that the Thevenin voltage is equal to the control voltage, so we can just write this as 3V Thevenin divided by 2000. And if you solve the system of equations, V Thevenin equals negative 500I, and I equals 5 minus 3V Thevenin over 2000, I think it's easiest just to plug it in my calculator, but you can solve it by hand if you wish, and you're going to get V Thevenin is equal to negative 5 volts. If you're confused by this, just look here at our V. This is our control voltage for our dependent source. So that's how we can determine that that point is indeed our Thevenin voltage. So we're going to draw a short circuit element between A and B. So we'll draw a label for our short circuit current. So when the terminals A and B are shorted together, the control voltage V is now reduced to 0. So now, since it's 0, our dependent voltage source is now going to be deactivated. So now with that controlling source deactivated, we can easily solve for I, which is our control for the current, which will simply be V1, which is 5 volts, over 2K ohms, and you'll be equal to 2.5 milliamps. So solving for the short circuit current, ISC, we're going to take a look at the circuit, and the short circuit, the current is going to take the least resistive path. So all of the current is going to go through the short circuit. Therefore, all of the current from the dependent source is going to appear in the short. Therefore, you're going to have negative 20I from the dependent source. It's going to be the only thing going through the short circuit. So if we plug in I into this formula, you're going to have I of the short circuit is going to equal negative 20 times 2.5 milliamps, which is equal to negative 50 milliamps. And then finally, using our formula from before, we know that R Thevenin is equal to V Thevenin divided by current in the short circuit, which we found to be equal to negative 5 volts divided by negative 50 milliamps, and then we'll multiply by 10 to the third to get rid of that milliamps, and we'll get 100 ohms as our Thevenin resistance. So if we want to draw this Thevenin equivalent circuit, we'll have our 5 volt source, which is negative, so we're going to draw it in the reverse. Then we'll have a 100 ohm resistor, terminal A, terminal B. This is going to be 5 volts. We flipped it because it's -5. Furthermore, if we wanted to represent the circuit in the Norton equivalent, you would take the Thevenin voltage divided by the Thevenin resistance. 5 divided by 100, you have 0.05 amps, but it's -5, and you'll have -50 milliamps, like we found before with the short circuit current. So in this final example, you can find the Thevenin equivalent using a test source. So in this method, we can excite the circuit from the terminals A and B with either a test voltage or a test current source. However, in this case, if we apply a test voltage source, we will know the voltage of the dependent voltage source and hence the controlling current, I. So we're going to draw in our voltage source. We're going to denote it as VT for test. And then we know we'll have a current I of T. So now to find the Thevenin resistance, we're going to simply solve this circuit. So we'll have I of T is going to equal our test voltage over the 25 ohms plus our current dependent current source, which is 20I. And then next, we're going to figure out what our variable I is. And when we're doing this test voltage, when you add the test voltage, you deactivate all the independent sources. So with our source V1 now 0, we can easily solve for I, which is going to be equal to -3V T divided by 2000. In this case, we'll just write 2. So we'll have our answer in milliamps. And we use VT here because our test voltage is in parallel with R2, so it's going to have the same voltage in parallel, which is V, and that's our control voltage for our dependent source. So now using these two formulas, we'll find our Thevenin resistance, which is equal to the ratio of the test voltage divided by the test current, which is equal to 100 ohms, which is the same answer we got before. This concludes our video of Norton and Thevenin equivalent circuits. Be sure to like and subscribe, and check out our other videos for more circuit analysis techniques.